we've taken a class in mechanics. What is so special about fluid mechanics? And as we look at it, it's the introduction of that word fluid. So the question becomes, what is a fluid? So what we need to do is we need to ask ourselves, what is the difference between a fluid and a solid? Let's think about a situation. Can we build a bridge out of a fluid? Well, of course we can't. Because if we tried to build a bridge out of a fluid, since a fluid always takes the shape of its container, it would just fall apart. Now, we could freeze the water, turn it into ice, but then it's no longer a fluid, it's a solid. So, since the case is that we can't build a bridge out of a fluid, does that mean that fluids are not important to bridge building? Well, of course the fluids are important to bridge building. So if we think about a bridge sitting in the middle of something like the canal near campus, we have water rushing at the base of the bridge. So we have to worry about the force that the fluid is imparting onto that bridge. Well, there are other ways that fluids can affect a bridge, specifically air. So let me show you a video of a bridge where they did not. Sorry about that, technical difficulty, where they did not worry about the air fluids. So this is the Tacoma Narrows Bridge, and you can see that this is not a CGI video, this is from the 1940s. So the Tacoma Narrows, I believe, is in Washington, so they built this bridge over a river, and what happened is this is actually back in a bad time for engineers, because back in the 40s, a lot of engineering was just, oh, you need to build a bridge, you get this book, it tells you where you put everything. They didn't really do any analysis. They didn't really understand the analysis, and so they just built it out of the book. The problem is, as you can see this bridge going crazy, is the wind through the Narrows hit the resonant frequency of the bridge, which caused it to start to oscillate. In fact, as you look at it, it's great because this is a beautiful example of a sine wave in action in nature. So what happened is the wind started blowing, it hit resonance frequency, and it started going through the sinusoidal pattern. And from your strength of materials classes, you should realize this is not a good thing. And actually, yes, that dude that's walking on the bridge is completely crazy. I have no idea what's going on with him. But since they did not consider what was going to happen with the air fluid as they had designed this bridge, bad things happened. And so if you continue to watch this video, eventually it will go and hit failure. And we're just going to let that run until that happens. And so it fatigues and breaks off. And there you go. So obviously we do not want this happening to things that we design or we analyze, because things breaking is usually bad. So this one, fortunately, nobody was hurt on it, but it really did drive a vast conversation on how we did our civil infrastructure and how we design things. So now, actually, if you look at a modern bridge design, they're actually taking into account things like lift and resonance frequency as they do it. Okay, so let us go and look at our fluids and our solids and our definitions of what's going on between the two of them. So it's really all about molecular spacing. So if we look at the top here, as we increase the molecular spacing, so we go from the left to the right, well, our intermolecular forces are decreasing. So the farther apart these guys get from each other, the less force that they have holding the two of them together. So as we look at it, we know that there are three states of matter. Well, actually, there's a fourth state, but we're not going to deal with plasmas in this class. And so you have a solid, a liquid, and a gas. And so the big difference between the three of them is we look at a solid. Solid has a set volume. All the molecules are holding together. They keep it in one shape. You can deform it. It's not easy to deform, but you can push on it and get a static deflection. So a liquid will take the shape of its container. Liquids are very easy to form because they're really easy to move around. Now, the one thing with a liquid to keep in mind is it has what's called a free surface. And a free surface is this interaction between a liquid and a gas. So anywhere you look, liquids will condense down, they will coalesce into an area, and they will be separated from the gas by what we call the free surface. So if you go outside of campus and look at the bay or the canal, you can see the free surface there. That's the surface of the ocean. So gases, they'll also take up their volume of the container, although, especially if you look at this picture here, if you leave the top off, well, the Earth's a big container, the stuff will run out and go away. Gases are easy to form, very easy to push around, but unlike liquids, they're very easy to compress. And they're easy to compress because we have a lot of space in between the different molecules. And there is no free surface because the gas will just keep expanding and going to wherever it's going to go. Now, liquids and gases all fall into the realm of fluids. They work very similarly, and aside from the ability to compress, the equations pretty much all work the same,